New notebook. LP example 1. I would say this is it would be a good idea for you to follow along, by the way, to actually type along. Example 1. Okay, so first, we're not going to use NumPy just yet. We're going to use Matplotlib. Import. If you're using Colab, this library is already pre-installed. So I'm going to go matplotlib.pyplot as plt. Quick question. How many of you are familiar with this library and have used it? If you know it and used it before, type in Y. Otherwise, type it in the chat. Okay, fine. Okay, I see some questions here. And one asks, don't you want to minimize the objective function? Don't you want to minimize the cost? No, right. In this example, we want to maximize the profit. Okay. If we sell these containers, we will earn cents on the dollar. So that's what we want to know. There's the cost associated with manufacturing them, and then there is the revenue we get from selling them. Notice how much we will profit. Okay. Of course, we can then turn this problem around and try to minimize the objective function if it had to do with the cost associated with it. But this is about maximizing profit. Okay. Okay. So everybody knows Matplotlib. I don't need to say much about that. But let me go ahead and plot this problem. So the first thing I'm going to do is generate a list of numbers. There is a method within, actually, I made a mistake. We do need NumPy. Import, but it's just to produce some numbers. Let me import NumPy. So X is going to be equal to NP dot, and we're going to produce a linear space. A linear set of values. From 0, that's the starting number, to, let's make it 100, and we want 2,000 numbers in this range. So this is a set of real numbers. 0, 0.1, 0.2, all the way to 1,000. Because the way we can produce a line on Matplotlib is to have a sequence of points, a sequence of XY points. So we need to trace along the X and Y axis. So we have X goes from 0 to 100. And I'm going to express the constraints as functions of Y. So let me give you the code. So here we are plotting the constraints as equations, obviously not equalities. How do we get this? How did we get this function? Well, if I come down here, it's this one. What we have done is we have moved 200 to the right side of the equation. So we get 4,000. Obviously, I'm not including the million. I don't want a graph that is that large. I will label in the graph. I will label in the X and Y axis, but I'm dropping the scientific notation from here. But it is 100Y equals 4,000 minus 200X. So 4,000 minus 200 times X. And then to get rid of the 100, I'm going to divide both sides of the equation. So if we divide both sides of the equation, let me actually make this y sub 1 and y sub 2. Okay, make it less confusing. So to get rid of the 100s, I'm going to divide both sides of the equation by 100. Divide this side of the equation with 100, you get y1, you get, and divide this side of the equation you get y2. Okay, so I am re-expressing these constraints as functions of y. I'm doing the same thing here. I'm moving 100 to the right side of the equation, so we get 3000 minus 100. So 3000 minus 100, and then of course to get rid of the 100, I'm going to divide both sides of the equation. Okay, and then I need to set the limits of my plot. Matplotlib would automatically set the limits on the x and y axis, but I want to maybe leave some room for visualization. Then I'm going to plot both of these equations. I'm going to plot both of these constraints. This is going to be y sub 1, and this will be y sub 2. Okay, I'm going to run this. So just to make it especially clear, this is the first constraint. So our solution area is limited to, this triangular region. But then when we involve the second constraint, now we are confined to this region. And you can see we have an intersection in here. We have just found this. We found this by finding the roots in our constraints. And we found out that the point on the feasible region is 10 and 20. So we can take this and we can plot it to indicate it. So whatever our objective function is going to be maximized to, it must not leave this area. Okay, so let me show you what I mean. And let me relabel this one. So for the first constraint, we have x must be greater than or equal to 0. So x must be greater than or equal to 0. And then y must be greater than or equal to 0. So plot the constraints. This is as equations, and this was supposed to be express the constraints as functions of y. All right. Now the point that indicates the feasible region. We use the plot method. The point on the x-axis, the point on the y-axis. And then here we can choose the marker and the size of the marker and give it a color. So plot the point indicating a feasible region. There we go. So our objective function must go through this point. Okay, so we're getting closer to the solution. And then let me show you how I can fill in the region. How I can fill in the regions. So I'm going to, there's a method called the fill between method. So we have y sub 1, y sub 2, and then we want to plot the region that where the points in our first constraint are less than the second constraint. Again, this is what it looks like. And it did not work because we have, okay, this was something else. This was supposed to be the masking area. So before we mask, Let me actually plot the gray area. So this will be fill between. So shade the regions under the constraints. So first we'll do the first constraints. That's y sub 1, which will give us that. And then I'll do for the second constraint. So y sub 2. Okay. And this other plot, let me disable this for a second. We want to get rid of these regions. So we should only see gray in the feasible region. And so what I'm going to do is I'm going to mask these areas. So I'm going to use the fill between method again, but I'm going to set the color to white and the alpha to 1. Now I will do this for both of the